Hello everyone, in this course we will learn transfer function of the sample system. First objective, define the transfer function of discrete time system, model, sampler and data holder using transfer functions, and obtain the transfer function of the sample system. What is the transfer function of a continuous linear system? If you remember, we have the input UAT, this is the G is a transfer function, and this is the XAT, this is the output of the system. That means the output of the system, the XAT, will be integration 0 to t G tau U t minus tau d tau. In the frequency domain, if you remember, we take the Laplace of the X, then Laplace of the G, Laplace of the U. Or you can write the XS equal to GS US. Laplace of the X exactly the same as the Z transform of the X. And XS exactly the same as the XZ. This one I will remind you in the next slide. G is the transfer function of the system, and the G is a called impulse response of the signal too. That means XT will be G tau Dirac t minus tau d tau. As you remember, any signals multiply of the Dirac, they have an answer about the G tau. This is G tau. The transfer function G is a Laplace transformation of the impulse response G. Usually a continuous system is modeled by the ODE, so that the obtain of the transfer function is associated to the system. Take the Laplace of the transfer functions, then rearrange and take the Laplace of the output divided by input. This is a general thing we do. For example, if you have the y dot t plus, for example, 3 y dot t equal to UAT, imagine if the YAT is the output and the UAT is the input, they ask me the transfer function of the system about the YS divided by US. You take the Laplace of this, become S to YS plus 3S YS equal to US, and YS divided by US will be S2 plus 3S and 1. That's easy. But what is the transfer function of the discrete system? My input is a UAK, G and XAK. I remember here is UAT, here will be XAT, just only change the key by T. The definition will be XAK will be sum of the J equal to 0 to K, J equal U K minus G, and in the Z domain you can write the Z transform of the X equal to Z transform of the J, Z transform of the U. This Z, that means we are in the Z domain. This is a Z transform of the X, the same as the Laplace of the X. Or you can write the XZ equal to JZ, UZ. G is called the transfer function of the system. G is called the impulse response of the signal to XK equal to sum of the GJ Dirac K minus J. This one become GK. Usually a discrete system is modeled by the differential equation. That means we take the Z transform of the differential equation, rearrange the term, then you find the Z out by Z in. I give the example, for example, U or Y K plus 2 minus Y K minus 1 equal to U K. YK is output, UK is input. We take the Z inverse from Z minus Z plus 2 YK minus Z I put here plus 1 is a plus 1 y equal to uk. Output divided by the input is equal to z2 minus z is 1, or I can write the z y z u. Be careful, transfer function of the system continuous or discrete, Laplace or Z transform of the signals, and let xk be signaled with the following Z transform. Sometimes we can consider that xk is the output of the virtual system G with the unit impulse system, because if you remember, the Z transform of the Dirac is 1. You can write the Z output divided by Z u, and the u is impulse is 1. You can rewrite something like this. Example, give the transfer function of the system below, and they ask you to find the transfer function about the two systems. This is the in the continuous term, this is discrete, and this is discrete. Just easily you can take the transfer function about the system with taking the Z transform and the Laplace transform. First of all, I take the Laplace, I find the transfer functions, and I take the Z transform of the signals, I find the transfer function in the Z domain. Here, sorry, this is the Z, is not the S. And taking the Z transform by considering the initial value will be, you add this part of the sentences, but I can tell you for the taking about the y k plus n, you can use the only z power n y k. Use the bilateral of the system. Same definition for the pole and the zero in the time domain will be see in the z domain. Only the different rule for the stability of the jury criterion. All the block diagram reduction method can be used for the discrete transfer function. Mason rules is still applied for the transfer function. We will not repeat the Mason rules. We will not repeat the reduction models. Only we give another method for the stability. And this is true when all the blocks are discrete, and what happens when all the continuous, and this is the grid time block. This one we will see together.